We're going to discuss some axioms for fields. But before we do so, let's try to recap some ideas that will help motivate why we might want to do this. Recall that we've introduced some notation because there are various sets that we'll want to study throughout the course. First, we introduced the idea of the natural numbers. This we denoted by the letter bold N. Here, this just consists of the positive integers because for this course, we will not consider the number 0 to be a natural number. Next, we have the integers that we denote by bold letter Z. This here is coming from the German word for number, which is Zahlen. Next, we have the rational numbers, Q. This just represents the quotients of our integers. Next, we have the real numbers that we'll denote by bold letter R. We're going to eventually come back and try our best to rigorously define what a real number is. And finally, we have the complex numbers denoted by the bold letter C. Again, we'll come back and rigorously define what a complex number is. We have seen that the natural numbers do have various properties. For example, a prime number p is an integer, at least 2, such that its only divisors are 1 in itself. And a composite number n is a number that is not prime. That is, it has two divisors, n1 and n2, whose product is n, and each divisor is neither 1 nor the whole number n. We found that there were 4 properties of interest once we look at prime numbers and composite numbers. First, let's say that capital N is the product, n1, n2, of two integers which are relatively prime. Well, if d is a divisor of n, then we can write d as the product of two numbers, d1 and d2, that are relatively prime, and d1 and d2 divide n1 and n2 respectively. Next, if a prime p divides n, which is a product of numbers n1 and n2, then either p divides the first product n1 or the second product n2. Third, every positive integer can be uniquely factored as a product of prime powers. And fourth, there are infinitely many prime powers. The second statement here is what's known as Euclid's lemma, and the third statement is what's known as the fundamental theorem of arithmetic. Now, we've seen properties here of the natural numbers, but what are some properties that the rational numbers Q, the real numbers R, and the complex numbers C satisfy? In fact, what is the definition of a real number anyway? Well, we know that the real numbers and the rational numbers satisfy at least 3 big properties. First, there's addition. That is, the sum of any two rational numbers is a rational number, and the sum of any two real numbers is a real number. Next, there's multiplication. The product of two rational numbers is a rational number, and the product of two real numbers is a real number. Third, there's ordering. Any rational number or any real number x satisfies either x is positive, x is negative, or x is 0. Simply put, we wish to generalize these properties. So to this end, we're going to define a field as a triple consisting of a set F, addition plus, and multiplication times, if it satisfies the following 10 axioms. We're going to try to place these together into 4 groupings so you can get a better idea of what these 10 actually do say. First, there's the idea of closure. That is, given any two numbers x and y, the sum is back in our set F, and the product is back in our set F. Next, we have various properties of addition. Given 3 numbers x, y, and z, we see first that the order in which we add 2 of them doesn't matter. That is, x plus y is equal to y plus x. Next, the order in which we group them does not matter. So first we could add x plus y and then add z, or we could add y plus z and then add x. Next, there should exist a 0 element, something we're calling an additive identity. What we mean is x plus 0 should be x for all numbers x. And finally, every x should have an additive inverse that we'll denote by negative x. That means x plus negative x should be the additive identity 0. We'll have similar properties for multiplication. So given any 3 numbers x, y, and z, in F, we'll say first that the product order doesn't matter. So x times y is equal to y times x. Next, the order of grouping doesn't matter. So first we could take x times y and then multiply by z. Or we could take y by z and then multiply by x. Next, there should exist a multiplicative identity that we'll call the number 1. That means x times 1 should be x for all x in F. And finally, we should have multiplicative inverses, but we want to be a little bit careful here. For all non-zero x, there should exist an x inverse, that is, x times x inverse should be 1. And the final property that we need is one that relates addition and multiplication together. So this says that if I take y plus z and then multiply by x, that's the same as taking x times y and then taking x times z and adding those two resulting numbers together. Again, a field is a triple that satisfies all 10 of these axioms. So let's give some remarks here that will try to explain some properties of what we're seeing. Well, if F is either the rational numbers, the real numbers, or the complex numbers, these are each examples of fields. However, neither the natural numbers nor the integers form a field. Well, what's a little bit strange here is that of the 10 axioms, 7 of them do hold. F1, F2, F3, F6, F7, F8, and F10. However, it's axioms F4 and F5 that give us trouble. F4, you'll recall, is the additive inverses. That is, if I have a natural number, its negative does not exist as a natural number. F5 is the idea of 1, that is, a multiplicative identity. Unfortunately, F5 certainly does not hold either. Similarly, for the integers, F9 does not hold, that is, multiplicative inverses, because the natural number 2 is an integer, but the inverse, 1/2, is not an integer. So we see that neither the natural numbers nor the integers form a field. In fact, if we wanted to try to write down more exotic examples of fields, then we see that the smallest type of field we could write down has to have 2 elements. In fact, it has to have at least a 0 and at least a 1. What's really curious is that we can write down a very abstract concept by simply defining a field as a set containing 2 elements, 0 and 1, where you can see here on the slide, we'll define addition one way and we'll define multiplication in a different way. And now it's a matter of checking that with this set F, this addition plus, and this multiplication dot, that we actually do have a field. You may be wondering about these 10 axioms and whether the 10 of these are really all that necessary. Well, actually, mathematicians like to study objects where perhaps not all 10 of these hold. You could take a look at various collections of those that hold and those that don't. You can see here on the slide various examples of different objects that mathematicians would study based on how many of these 10 axioms hold. You might see some of these concepts in an abstract algebra class at some point. Now, we've listed some examples of fields, and we've listed the axioms that we'd like to hold to be true, but now we'd like to focus on some statements that we can prove to be true based on these various axioms. Well, let's consider in particular axioms F4 and F8. F4 says something about having an identity under addition, and F8 says something about having an identity under multiplication, namely the existence of 0 and 1, respectively. What we'd like to do now is prove that 0 must be a unique element and 1 must be a unique element. In a field, the additive identity 0 is unique. Here's how we prove this. Let's assume that our field does exist. We have a set F, addition plus, and multiplication dot. We know that there exists at least one additive identity because axiom F4 is true. Since we want to show uniqueness, let's say that we have perhaps two additive identities. Let's call them 0 sub 1 and 0 sub 2. We're going to use the axioms we saw before to actually prove that these two additive identities must be the same. Well, let's first start with the idea that 0 sub 1 has to be 0 sub 1 plus 0 sub 2 because axiom F4 asserts that x plus 0 sub 2 equals x for all x in f. So it certainly holds if x is equal to 0 sub 1. Next, we can interchange the order of 0 sub 1 plus 0 sub 2 because axiom F2 says that we have commutativity, that is x plus y equals y plus x. Third, we see that 0, 2 plus 0 sub 1 equals 0 sub 2 because axiom F4 asserts that x plus 0 sub 1 equals x for all x in f. So staring here, now we see that 0 sub 1 indeed does equal to 0 sub 2, so our additive identity must be unique. We're going to have an exercise in class later as a group exercise to show that the multiplicative identity, the number 1, is also unique, pretty much using the same set of steps as above. It turns out that we can do this same concept if we replace the additive identity with additive inverses. Let's recall that in a field, an additive inverse means that if you were given x in f, then you should have an element y such that x plus y is equal to 0. Y would be the additive inverse of our element x. We know that there exists at least one additive inverse. We want to show that this must be unique. So let's say maybe that there are two, y sub 1 and y sub 2. We will prove that y sub 1 equals y sub 2. Here are the set of steps. First, we just shown that the additive identity 0 is unique, so we can say that y sub 1 equals y sub 1 plus 0 by axiom F4, additive identity. We now know that 0 can be replaced with x plus y sub 2 because axiom F5, namely additive inverses, show that y sub 2 exists. Now we can use associativity, namely axiom F sub 3, to move around our parentheses, and then we can use axiom F sub 2, commutativity, to move around the order. So that means we have parentheses x plus y sub 1 in parentheses plus y sub 2. Finally, we can use commutativity again, that is axiom F sub 2, to swap around y sub 2 to bring that up front, and finally use the fact that we have additive inverses again to know that x plus y sub 1 has to be 0. Using now the additive identity property f sub 4, we see that y sub 2 plus 0 is y sub 2, and we're able to conclude that y sub 2 does indeed equal to y sub 1. So again, we know that our additive inverse must be unique. We'll leave it as a group exercise to show that multiplicative inverses are also unique in the same fashion. Thanks for listening.